Welcome back. In this video we're going to tackle some intriguing problems that will give you a solid grasp of the center of mass and how it behaves under the influence of external forces. Before we dive in, I highly recommend watching my previous video on the center of mass. It's packed with essential insights, and the link is right up on the screen. Let's begin with our first question. We are examining a system consisting of 2-point masses, 2 kilograms and 6 kilograms. These masses are positioned at distances of 2 meters and 8 meters from a reference frame, as shown in the illustration on the screen. Our objective is twofold: first, to determine the distance to the center of mass from the reference frame, and second, to find the distance to the center of mass from the 2 kilograms mass. This is the expression we derive to find the distance to the center of mass along a straight line, relative to a reference frame. Here, we have 2-point masses positioned along the x-axis, meaning the center of mass for each object is also on the x-axis. To determine the center of mass of the system, we first sum the masses, which in this case are 2 kilograms and 6 kilograms. Regardless of the location of the reference frame, it is essential to obtain the total mass of the system, which will be used in the denominator of our calculation. Next, we calculate the contribution of each mass to the center of mass. The 2 kilograms mass at 2 meters contributes 4 units, and the 6 kilograms mass at 8 meters contributes 48 units. Summing the contributions of each mass, which amounts to 52. We then divide this sum by the total mass of the system, which is 8 kilograms. This calculation reveals that the center of mass is positioned at 6.5 meters from the starting point, along the x-axis. Before we continue with the next part of the question, let's mark this distance on the diagram. This step is important, because it will help us understand the comparison between this distance and the second distance of the center of mass that we will calculate next. Alright, now we'll shift the reference frame to the position of the 2 kg mass. By doing this, we are essentially considering the 2 kg mass as the origin of our new reference frame. From this new perspective, we will measure the distance to the 6 kg point mass. The distance between the 2 kg mass and the 6 kg point mass is 6 meters. This means that in our new reference frame, the 6 kilograms mass is located 6 meters away from the origin. We will follow the same approach as we did before, to calculate the center of mass, but this time the reference point is located at the 2 kg mass. The point that you should remember is that, even though the reference point is on the 2 kg mass, and distance to the center of the 2 kg mass is 0, we take the mass of the 2 kg when taking total mass of the system. This result shows that the center of mass is 4.5 meters from the 2 kg mass, which is the same location we worked out before. The center of mass is a point that signifies the average position of the entire mass of a system. Its location is determined by how mass is distributed within the system, and is independent of the choice of reference frame. This implies that regardless of where one places the reference frame, the center of mass maintains the same relative position in relation to the masses within the system. Let's proceed to the next question. Displayed on the screen is a uniform wooden square prism, weighing 4 kg. It's understood intuitively that the center of mass for this block is situated at its midpoint. A smaller square prism, weighing 1 kilogram, is taken out of this block. Our goal is to determine the center of mass of this remaining 3 kg section of the wooden block. As the first step, we need to define the reference frame. This reference frame will remain fixed until we find the center of mass of the 3 kilograms block. It is crucial to place the reference frame in a way that simplifies subsequent calculations. If you choose a reference frame without careful consideration, finding the center of mass of the system can become exceedingly difficult. So, what factors should you consider before identifying the reference frame? Based on my experience, I recommend following these steps when deciding on the placement of the reference frame. Symmetry of the system. First and foremost, Choose a reference frame that aligns with any symmetry present in the system. This can simplify the calculations by allowing some components to cancel out. In this example, we can consider the symmetry about the x-axis. By placing the reference frame along the x-axis, we can eliminate the need to calculate the distances from the y-axis and the z-axis. This approach reduces the problem to a one-dimensional calculation, making it much simpler to find the center of mass. Origin of the coordinate system. The position of the origin can affect the complexity of the calculations. Often, placing the origin at a point of symmetry, or at one of the objects in the system, can make the math more straightforward. Type of motion. If the system involves moving objects, selecting a reference frame in which one or more of the objects are at rest can simplify the analysis. External forces. Consider whether external forces act on the system, and how these forces might affect the center of mass. In some cases, an inertial reference frame, one that is not accelerating, might be preferable. Convenience and simplicity. Choose a reference frame that makes the calculations as simple as possible. This might mean selecting a frame that reduces the number of variables, or makes certain integrals easier to solve. Relative motion. If analyzing the relative motion between objects, it might be beneficial to use a reference frame that moves with one of the objects. Dimensionality of the problem. The complexity of the reference frame can also depend on whether you are dealing with a one-dimensional, two-dimensional, or three-dimensional system. Choose a frame that best matches the dimensionality of the problem for simpler calculations. Practicality and measurement. Consider how measurements will be taken, and choose a reference frame that aligns with the practical setup of the experiment or observation. This is simply a guideline to help you establish the reference frame for locating the center of mass and analyzing the system's behavior. However, you have the flexibility to select the most suitable reference frame to determine the attributes and the center of mass of a given system. With that said, we shall now proceed to the question. In this example, we have positioned the origin of the reference frame at the center of mass of the composite box, marked as O. By doing so, we can greatly simplify the problem by leveraging the system symmetry. Each side of the composite block measures 8 centimeters. The 1 kilogram block is a square prism, with its center of mass positioned at the block's midpoint. When referenced to the frame, it lies 2 centimeters from the origin. Due to the symmetry of the 3 kg block, its center of mass naturally aligns with the x-axis. However, because the entire system is symmetric and balanced around the origin, the center of mass of the 3 kg block is positioned to the left of the origin. Let's denote this position as x sub b. We can further simplify this problem by treating the center of mass of each block as a point mass located on the x-axis. This approach means that instead of considering the entire volume and shape of each block, we assume all their masses are concentrated at their respective centers of mass. This simplification reduces the complexity of calculations and facilitates the analysis of the center of mass of block B. We have now reduced the complexity of this problem, making it similar to the previous example we did. However, instead of finding the distance to the center of mass, we need to determine the distance to one of the point masses that comprise the system. As before, we can apply the expression to calculate the center of mass along the x-axis. The calculation becomes much simpler, because we have placed the reference frame at the center of the composite block, making the distance to the center of mass 0. Let's substitute the available data, and derive an expression to find the distance to the center of mass of block B. Please remember, any measurement taken to the right of the reference frame is positive, and any taken to the left is negative. This calculation shows that the distance to the center of mass of the 3 kg block is 0.67 centimeters to the left of the reference frame, Let's proceed to the next example. Consider three objects with masses of 2 kg, 4 kg and 10 kg respectively. Their position vectors, expressed in meters, are as follows. Our task is to determine the position vector of the center of mass of these three objects. To find the position vector of the center of mass, we use this formula. We discussed this formula in detail in my previous video. Please check that video if you need to know how it was derived. You can find the link to that video at the top of the screen. First, we will calculate the total mass of the system. It turns out to be 16 kilograms. Next, we calculate the weighted sum of the position vectors. By substituting the given values, we get the following. Expanding and simplifying the vectors, we obtain this expression. By combining like terms, we simplify the expression as shown here. Now that we have calculated both the weighted sum of the position vectors and the total mass of the system, we can find the position vector of the center of mass by substituting these values into the above formula. This final result gives us the position vector of the center of mass for the three-object system, clearly indicating the center of mass's location in the coordinate space defined by the unit vectors. Okay, let's move on to the next example. Here, we will find the center of mass of a uniform triangular prism, like the one displayed on the screen. The concept of the center of mass applies to both discrete and continuous systems. Thus far, we've discussed finding the center of mass for discrete systems of masses. However, the same principle extends to continuous bodies, like the one shown here. For a system of discrete particles, the center of mass is the weighted average of their positions, where the weights are their respective masses. Similarly, for continuous mass distributions, the center of mass is determined by integrating differential mass elements. The integral represents the weighted sum of these elements, where m is the total mass of the object and dm is the differential mass element. Alright, with that backdrop, let's move on to finding the center of mass of this prism. To derive the expression for the coordinates of the center of mass, let's use the following notations: L for the length, h for the height, and w for the width of the prism. For a uniform rectangular prism, the mass is evenly distributed throughout its volume. We will denote ρ as the density of the prism, which is defined as the mass per unit volume. The approach we will first take to find the center of mass requires calculus. However, I will show you a much simpler method in the following section, which does not require advanced mathematics to find the center of mass of a prism. As we have done previously, we will begin by identifying a reference frame for our measurements. Then, we will consider an infinitely thin strip along the x-axis with a height of y and a width of w. The mass of this strip is determined by its cross-sectional area multiplied by its width and the density ρ. The area dA is given by y multiplied by dx. Since it is very small, we can approximate it as a rectangle. Now, let's combine these two equations and write an expression for dm. Alright, now we can consider the slope of the prism and formulate a function to express y in terms of x. Given the height h of the prism and its length l, we can determine the slope of the line. In our chosen reference frame, a negative gradient indicates a downward slope. The line intersects the y-axis at a height of h units. Using this information, we can express y as a function of x. Next, we need to find an expression for the total mass of the prism. The density ρ of the block is defined as mass over volume. Therefore, we can express mass in terms of density multiplied by volume. The volume of the prism is given by the area of the triangular cross-section, which is half the height multiplied by the length. To get the volume, we multiply by the width, which results in this expression for the mass of the block. Now, we have all the information needed to find the distance to the center of mass. Due to the symmetry of the block, we know the center of mass is halfway along the width. However, we still need to determine how far the center of mass is, along the length and height of the prism. We will first find the distance to the center of mass, along the length of the prism. For that, we will use this equation. Next, we will substitute the expressions we derived for mass and dm. This can be simplified to what is shown on the screen, omitting the density ρ, and width w. In place of y in this expression, we can substitute the function that we derived for y, in terms of x. We can eliminate the brackets, and expand the expression. After that, we can further simplify it by cancelling out the height h. We are left with an expression that includes only the length L of the prism. At this point, we can take the integral of the expression, which yields the following function. Now, we can apply the limits to the integral, resulting in this expression. We can then further simplify it, to obtain the final solution, which gives us the distance to the center of mass of the prism, along the x-axis. To determine the center of mass, along the height of the prism, we can rotate the prism, and follow the same steps as before. This process will demonstrate that the center of mass along the height is located at 1/3 of its total height. When considering the symmetry of the block, the center of mass along the width of the prism should be at its midpoint. Therefore, we can conclude that the coordinates of the center of mass of the prism are 1/3 of its height, 1/3 of its length, and halfway across its width. Keep in mind that these coordinates of the center of mass relate to the reference frame we have chosen. We will now explore another method to find the center of mass of this triangular prism, which is much simpler and quicker. Just as there are many ways to skin a cat, there are various methods to determine the center of mass of a triangular prism beyond these two. As we did previously, we will define a reference frame. We know that the center of mass along the width is halfway across. What we now need to determine is the distance to the center of mass along the length and height of the prism. If you consider the rectangular face of the prism, its center is located at half its height. Now, let's examine all the cross-sections along the length of the block. The center of each section is at the midpoint of the vertical lines. Combining all these midpoints forms a line, as illustrated here. The center of mass of the prism should lie somewhere on this line. We can follow the same steps and draw another line to the horizontal face of the prism, as shown. It goes without saying that these two lines intersect at the center of mass of the prism. Let's denote the coordinates of this point as x and y. Using the defined reference frame, we will now express the equations of these two lines. The first line starts from the midpoint of the height and has a slope equal to half the height divided by the length. However, it slopes downward towards the x-axis, resulting in a negative gradient. This line intersects the positive y-axis at half the height of the prism. With this information, we can derive the equation of this line. Applying the same approach, we can then derive the equation of the second line. The center of mass is found at the intersection point of these two lines, which is common to both equations. Since ycm is common to both equations, we can equate them and solve for xcm. This calculation yields the same distance to the center of mass along the length of the prism, as previously determined. Substituting the calculated value of xcm into either of the equations allows us to find ycm. Therefore, irrespective of the method used, the distance from the center of mass to the x and y axes remains 1/3 of its length. Before we proceed with the video, I would greatly appreciate it if you could kindly give it a thumbs up, subscribe to my channel, and activate the notification bell. Your support means a lot. Thank you. Now, let's get back to the video. In this next example, a 1 kilogram ball moves at 2 meters per second on the deck of a 200 kilograms boat. First, determine the velocity of the boat relative to a post on the shore. Next, find the velocity of the boat relative to the ball. In this scenario, neither the ball nor the boat is subjected to an external force. Therefore, the velocity of the center of mass must be 0. You might think that there is a force between the ball and the deck of the boat, and that is correct. However, when considering both the ball and the boat as one system, this internal force cancels out. In the absence of an external force, the momentum of the system is conserved. Therefore, we can apply the law of conservation of momentum to find the velocity of the boat relative to a point on the shore. If we take m1 and v1 as the mass and velocity of the ball, and similarly m2 and v2 as the mass and velocity of the boat, then by substituting the given values, we can find the velocity of the boat with respect to a point on the shore. The negative sign indicates that the boat's velocity is in the opposite direction to the ball's motion. You should remember that, when applying the principle of conservation of momentum, the velocities of the objects involved are measured with respect to a fixed reference frame. More precisely, the total momentum of a system is conserved when no external forces act on the system, and all velocities are measured relative to an inertial reference frame. An inertial reference frame is one that is not accelerating, meaning it is either at rest or moving with a constant velocity. To determine the velocity of the boat with respect to the ball, we need to change our reference frame to one that moves with the ball. This means that instead of observing the system from a stationary point, such as the shore, we now imagine ourselves moving alongside the ball at the same velocity as the ball, which is 2 meters per second to the left. We have already calculated the velocity of the boat with respect to the lab frame, which is 0.01 meters per second to the right. In this context, the lab frame is our original stationary reference point, like the shore. To calculate the velocity of the boat with respect to the ball, we use the principle of relative velocity. According to this principle, the velocity of an object with respect to another moving reference frame is determined by subtracting the velocity of the reference frame from the velocity of the object measured in the lab frame. Mathematically, this can be expressed as shown here. So, substituting the values, we get this expression. This result indicates that from the perspective of someone moving with the ball, the boat is moving in the opposite direction, at a velocity of 2.01 meters per second. For a more detailed explanation of this concept, and to see it demonstrated visually, please refer to my previous video. Alright, let's examine this final example in the video. I will upload more examples in the coming months to further clarify the concepts covered in this section. Here, we have two spherical objects with masses of 3 kilograms and 2 kilograms, connected by a weightless spring, with a specified spring constant. An impulsive force is applied to the 3 kilograms mass, resulting in a velocity of 6 meters per second. Our goal is to determine the velocity of the center of mass. An impulsive force acts briefly, but with a high magnitude, altering the object's momentum. typically associated with collisions or impacts. This force affects the object intensely, but momentarily. Following the impulse, the 3 kg mass moves uniformly in a frictionless environment, with no external forces. Immediately after the impulse, the spring between the masses remains unstretched, indicating no immediate change in its length or tension. The initially stationary 2 kg mass does not move immediately post-impulse. However, an internal force via the spring acts between the masses. The center of mass gains velocity immediately, due to the external impulse. This change is a direct result of the impulse, affecting the system's momentum. Denoting the masses and velocities of the 3 kg and 2 kg spheres, as m1v1 and m2v2, we calculate the center of mass velocity, VCM, using this formula. Substituting the given values, we determine the center of mass velocity as 3.6 meters per second. This calculation applies conservation of momentum and center of mass principles accurately, showing how the system's center of mass responds to the applied impulse and the velocities of both masses. Thank you for watching this video in its entirety. I trust you found these examples both informative and valuable. If you haven't subscribed yet, please consider doing so to stay updated. Until our next video, take care, and goodbye.